Hey, good morning, everybody. This is Mr. Aynesworth, and we're going to get into a little mind map here, putting together all the concepts for the cubic function. We're talking about the third degree polynomial function. So what I did was I chose some cubic functions to work with here. I chose the two parents, mom and dad. All right, we're talking about y equals x cubed on the upper left. We'll call that, we'll just call that mom, I guess. All right, and then we'll take a look at y equals negative x cubed. We'll just refer to him as dad. And we'll also take a look at some offspring here. All right, we're talking about variations of mom and dad here that have been shifted, okay? And also the relative min and max here have also been shifted, and just some transformations of them too as well. Okay, so let's get right into it. Let's take a look at mom first, y equals x cubed. Let's go ahead and graph that function first so we can take a look at it here. So when x is 1, y is 1. When x is negative 1, y is negative 1 here, so I can get a general idea of what this thing looks like. And it's a special curve that we've seen before. There's your x cubed function. Now, polynomial functions are continuous. They don't have any holes or asymptotes. And so the domain for all polynomial functions is a set of reals. And you could use some internal notation as well. So when we say all reals, we're talking about from negative infinity to infinity. It also goes infinitely up and down, no holes, no asymptotes, and so its domain is all reals as well. The range is a set of all reals from negative infinity to infinity. Okay, now the cubic function has a special point called the inflection point at the origin, right here, and that's at 0, 0, where it changes concavity and where it changes from concave down to concave up. Okay, so from negative infinity to 0 is concave down. From 0 to infinity is concave up. So let's talk about that because that implies something. So on this first interval from left to right, okay, so on, let's say, negative infinity to 0, all right, this arrow means implies it's concave down. What does that mean? Well, that means that the average rate of change is decreasing over that interval. Okay, and that comes from unit 1. Now, from 0 to infinity, something different happens. Okay, it changes concavity. All right, it's concave up. And that implies that the average rate of change, all right, is increasing on that interval. Okay. A couple other facts that we know. So we talked about limit notation as well. So in quadrant 1, notice that as x goes to infinity here, the graph goes up. So y goes up to infinity here because it goes to the upper right. Because of that, I can say that the limit of the function as x goes to infinity, so the limit of the function is called f of x, right here is infinity because when you go right, that's what happens when you go to infinity here. The function goes up. On the left side, if you go left, okay, as x travels to negative infinity, the function goes down. So I can also say that the limit as x goes to negative infinity, okay, so the limit of the function, f of x, as x travels to negative infinity here, since it goes down, the limit is negative infinity because it simply goes down versus up. So when you go left, the function goes down. When you go right, the function goes up. All right, and you can see that from the graph. And these aspects right here were on the quiz, on the last quiz. And so what you need to do when you mind map something and when you put all the ideas together is you need to take everything you learned and apply it to the concept. And in this case, I'm talking about cubic functions of 4 different types. So let's go to the other parent, okay, Daddy-O here, and let's graph him. All right, so when x is 1, y is negative 1, so it's down, Let me plot that again. 1, negative 1 is over here. All right, when x is negative 1, y is positive 1, so he looks a little bit different. His behavior is different, and that's typical of mom and dad, right? Right, okay. And then, there we go. So there's Daddy-O right there. There's negative x cubed. And notice that it looks a little different, all right, compared to mom. Okay, it's curved differently. The end behavior is different. Okay, the end behavior is different, and that's typical of mom and dad. They're different people. And these are different functions, but they have similarities. Okay, now again, as I said earlier, the domain is all reals, okay? You can say from negative infinity to infinity. The range is all reals from negative infinity to infinity. That's because there's no holes or asymptotes because these are continuous functions. All right, you can trace them with your pencil, all right, without lifting your pencil off the paper, okay? Now, it also changes concavity. So from negative infinity to 0, it's concave up, and then from 0 to infinity is concave down, and that has implications. So let's go through it again. So from negative infinity to 0, again, look left to right. It's concave up. That implies something here, okay? Now, when a function's concave up, we're talking about the average rate of changes increasing on that interval. Okay, I and C is increasing. Now, from 0 to infinity, it changes concavity. So here it's concave down. What does that imply? It implies that the average rate of change is decreasing. That's a Unit 1 concept. I'm not going to go over that in detail again. You just should know that. And if you don't, you obviously do a mind map on that and figure that out too. Okay, we talked about that extensively in Unit 1. So what else? Now let me see. Let's talk about the limits here because the end behavior is different. So let's discuss end behavior. Okay, so this over here on the left was a discussion of end behavior. So let's do that. Let's do that for dad, okay? So when you go left, the function goes up. When you go right, okay, when x goes to infinity to the right, the function goes down, okay? So what can I say? Well, I can say that the limit, okay, as x approaches infinity of the function here is negative infinity because when you go right on the graph, the function goes down. That's what these symbols mean. Now, when you go to the left, you're traveling to negative infinity. So the limit of the function as x approaches negative infinity, since the function goes up, it's positive infinity. So again, when you go left, it goes up. When it goes right, it goes down. This is the end behavior of your function. And that's an important thing. Okay, so that's mom and dad here. Let's talk about the offspring. Okay. Now, this first one here on the lower left, let's discuss him. So here, I'm going to put so A right here is positive 1, and that implies something. So when A, here, hang on, let me, oops. Okay, so when A is positive 1, this number right here, when A equals positive 1, the behavior of the function, I can already tell, it looks like this in general, okay? If A was negative, which it is on this last function here, it goes the other way, the end behavior changes. So this affects the end behavior of the graph, and that is a previous concept that we've talked about. And this is the thing that you guys need to do, is you need to study well and study like this so that you can take all the concepts you've learned and apply it to a particular function, all right, and describe all of its behavior. And all of its components. Like I look at this right here and x minus 1 to the second power. I know that I have a 0, okay, at x equals 1. Its multiplicity is 2. Multiplicity of 2, which means I have a bounce there. So again, I'm taking previous concepts and applying them. I also know that I have a 0 at x equals negative 2 that's raised to the first power, so the multiplicity is 1. Okay, and I know that it crosses the y-axis there. So given that right here, I can graph the function. Okay, so what I do is I graph the first 0 at 1. I graph the second 0 at negative 2. Okay, now it bounces at negative 2. And it crosses at 1. So it has to look, let me see. No, excuse me, it bounces at 1. So I have a bounce here. So it doesn't go through it. So it's got to go something like this. Bounce here, and then it's got to go through negative 2. It's got to look like something like that. Again, the end behavior. Because A is 1, I know it behaves like this. If A was negative 1, I would draw it a totally different way. Okay, speaking of end behavior, I know that the limit as x approaches infinity, this is infinity to the right, of the function here is positive infinity because it goes up to positive infinity. I know that the end behavior as x approaches negative infinity is negative infinity because it goes down. So it goes up to the upper right, down to the lower left, to negative infinity. So this is my end behavior right here. It's called end behavior. All right, now let's apply it to the other offspring. Okay, just talked about son, now let's talk about daughter here. Okay, so now I know, just by looking at this, I know that a here is -1. That means the function behaves like this right here. I just know that from experience. What else do I know? I know some zeros. I know I have a 0 at 0. Okay, there's a bounce there because there's a multiplicity of 2, so I know I have a bounce. And I know I have a 0 at 3. I know the multiplicity is 1, so it crosses there. So the multiplicity equals 1, and I have a cross there. So notice what I'm doing here. I'm analyzing first, and then I graph the function. I sketch it. Okay, so I have a 0 at 3. I have a 0 at 0. It's got to have a bounce at 0, and it's got to behave something like this. So if I graph the function here, it's got to bounce at 0 because it has a multiplicity of 2. So there's my bounce. But I got to go through it at 3, so it's got to come back down, right? And it's got to go through that 0 here. So it's going to look like that. And you could check that in Desmos, okay? Verify with Desmos, as I always say, okay? Or TID4, whatever you like to do, okay? And so in terms of the end behavior, as x approaches infinity here, this function, all right, approaches negative infinity because, again, it goes down. Right and down, left and up. All right, you can, it's that simple. So the limit as x approaches negative infinity, that's left, all right, of the function is positive infinity because, again, when you go left, the function goes up. When you go right, the function goes down. And that's called the end behavior. All right. And that's all there is to the mind map. You want to learn how to take a concept and write down everything you know about it and how it's all related. And that's what a mind map is all about. It's like a big brainstorm over a particular concept that you're working on. And I didn't do anything new here. You can pull all of this out of your main unit that we're working on and then put it all together. And that's a mind map. All right. This is Mr. Aynesworth. I'll see you in my next one. See you soon. Take care. Bye-bye.